Hey everyone, my name is Andrew Yates. I'm a professor here at UFA in the IR lab, and I'm going to be presenting the Neural Information Retrieval module lectures to you for this Deep Learning 2 course. Today, in this lecture, we have part 1 of the course. Here we're going to be looking at some of the background. So what is IR briefly? What is neural IR? Why neural IR? And then some of the first types of methods for performing information retrieval with neural methods. We'll get more into the differences between these methods and the ones we'll talk about later, but the very quick overview is the methods we'll look at today are very effective, meaning they work very well, but they're not necessarily so efficient. So part 1 will focus on background and these less efficient so-called re-ranking methods, and then part 2 will look at how we can address some of these limitations. We also, of course, have an accompanying tutorial for you. And this part 1 of the lecture corresponds to, I think, the 3 first parts of that tutorial. So BM25, Canoram, and the BERT re-ranker. So with that, let's get started. But before we do, a quick note. Much of this content and slides in this lecture will be drawing from this book, Pre-trained Transformers for Text Ranking, BERT and Beyond. I'm one of the authors of this book, but also I have these 2 co-authors, Jimmy Lin, Rodrigo Noguera from the University of Waterloo, who have, of course, contributed a lot to this material. So I'd just like to give credit to them, and also to point out that Rodrigo also has done quite a lot of work developing parts of these slides that I've taken and modified or just incorporated in various ways. If you're interested in this tutorial and want to learn more, interested in this lecture and want to learn more, you can take a look at the book. We have a version available on arXiv, and then there's also a publication by Morgan and Claypool. I believe you can access this open access or for free, not open access, through the UFA library. So with that, let's actually get started. It brings us to the outline. As I said, we're going to start with some introduction and background. So what is neural IR? We'll talk a bit about evaluation, so data sets and metrics, because as you know, many neural methods are supervised. And when we talk about supervised methods or any method, we need to know how to evaluate them and how to train them. So you'll give some idea of what data sets are commonly used. And then we'll jump into the actual, meat, so to speak, of this topic. So today we're looking at re-ranking methods, essentially methods that are not necessarily so efficient, but they can really improve ranking quality. But this all begs the question, of what ranking is, what information retrieval is. So let's start with this. So just to give a quick definition, given a piece of text, so this could be keywords, a question, a news article, some query, we want to rank other pieces of text. So these could be passages, documents, maybe other queries, ordered by their similarity to the piece of text. So web search is just a really common example of this that I think everyone is quite familiar with. So here we have a query, and the search engines are ranking documents in response to this query, ordered by their relevance to the query. Specifically, we're going to be talking about ad hoc retrieval generally in this module. So to tighten up the formulation just a little bit, here we're given a query queue. We're given some collection of texts. And we want to return a ranked list of these k texts, D1 through dk, ordered by some metric of interest. So for example, this metric is precision at 3, meaning we look at the top 3 documents. And out of those 3 documents, we see that 2 of the 3 are relevant. And so our precision at 3 is 2 over 3 or 0.66. There are, of course, other applications of information retrieval, other types of ranking problems. So just to briefly mention these, for example, question answering. Here we might rank passages in response to some question. And then maybe within the passage, we need to extract some answer span. This could be done with ranking or perhaps some sort of classification. And so you see here, we have a question, what causes precipitation to fall? And the answer has been identified in that passage. Text recommendation could also be viewed as a kind of ranking or information retrieval problem. So here on the left, we have this article. This article will serve as our query. So you see Andromeda and the Milky Way's black holes will collide. Here's how it will play out from Science News. And then given this article serving as a query, we might find other related articles to show in, for example, the sidebar on the web page, as is done on this website. So we see, for example, in the top right, there's an article about supermassive black hole gets kicked to the galactic curb that could be produced via ranking as response to this article. So this is a type of recommendation. So this is just a very brief overview of what we're going to be looking at, information retrieval. And really, I like to get things started with asking, why are we interested in neural information retrieval specifically? Well, there's a few reasons. First of all, as you're of course familiar with from Deep Learning 1, other courses, deep learning is very good at representation learning. So this can reduce the handcrafting we need to do when performing a retrieval. So for example, here on the right, we see a basic ranking method. So the left, IDF, inverse document frequency, is some collection statistic of a term. I'll give you more brief examples of this later. And on the right, we have term frequency. This is a document statistic. At a high level, IDF is saying how discriminative is a term. And on the right, term frequency is saying how important is a term to a document. So if you see, for example, a term like Andromeda or galaxy in a document many times, this is probably a good signal that it's important for the document, because on the left, we have a high IDF. For galaxy, it doesn't occur in most documents. And on the right, we would expect the term frequency for galaxy in this document or Andromeda in this document to be high. But these are just concepts. We have to instantiate them, and there are many ways to do so. So, for example, IDF can be defined as the log of the number of documents in a collection over the number of documents with the term, or maybe some variation of this. Many other ways to do it. Same thing with term frequency. You could take a straight count. You could try to do something like 1 plus the log of TF. There are reasons, theoretical reasons at least, to believe this is going to be a bit better, but I don't want to get into them, and so on. So you see there's many ways to do this, and we've just started with a very basic retrieval function. So clearly this is somewhere that representation learning should be able to help. Well, both representation learning and then some learning of a network to compute these scores directly. And of course, another big benefit, this is also connected to representation learning, is it gives us the ability to consider new signals. For example, soft matches between different terms. So you'll notice that this summation I briefly showed you in the previous slide was over terms in the query. And what this function is doing is for every query term, if it's in a document, the term frequency will be non-zero. And so we'll add some score to the score for that document. But always we're checking to see if a specific term is in the document. There's no notion of, for example, searching for galaxy and matching documents and instead say Andromeda, for example. We can only do exact matching. We could maybe improve this with more handcrafting. So for example, if you think of parts of different parts of speech of a verb, for example, like swim, swimming to swim, swam, these could all be collapsed to the same lemma via lemmatization, or more commonly stimming is used, which simply is less principled. But again, this would require some handcrafting to take swimming, remove the suffix, turn it into swim, some custom rule to take swam and make that swim, and so on. So we can better represent the terms in documents with this neural machinery, and that allows us to capture new signals and do some sort of soft matching rather than only exact matching of these query and document terms. There are, of course, non-neural ways to do this. I'm not going to get into them in this lecture. This is, of course, part of the Deep Learning 2 course. But for example, there are translation models or topic models like LDA, PLSI, if you've heard of these. And the really short answer for why neural IR is what I'm going to talk about today is that it seems to be empirically much more effective than these past approaches, or at least the way we produce neural IR models creates models that are much more effective. Perhaps there's a different way to do these. And just to give you, I said imperial effectiveness, so just to give you some idea of what I'm talking about here, I'll talk about evaluation metrics very briefly in the next few slides. Not so briefly, but in the next few slides. So here we have IRNet. This is a neural method, but it's not using transformers or BERT. I think people in this course are generally familiar with what these are, but I'm going to give a quick introduction a little later. If we go very far down to the bottom, we see BM25, which is a non-neural method. So the first thing to point out is we have a very big improvement moving from non-transformer based, so older neural methods, pre-transformer methods, to this transformer-based method, a very large increase. And we see an even bigger increase moving from, say, BM25 to the BERT-based method. So it's almost doubling this metric. You don't know perhaps what this metric is yet, but I can tell you that this is a very significant improvement. And we see the same thing on other test collections. So for example, looking at Robusto 4, which is another commonly used collection, These red dots are non-neural models. The blue dots are the beginning of neural models, essentially as we were figuring out how to build these. And then these green dots I just added are even more recent transformer-based models. So kind of the story here is we're starting to possibly see some improvement with the neural models. This is debatable. This is not a debate I want to get into in this lecture. But we see, with recent transformer-based or BERT-based approaches, there's very clearly very significant improvements over the non-neural models. I should mention that these non-neural models, the very top ones here, may be using human intervention. So for example, they may have humans that are helping rewrite queries, so to speak, whereas these neural models are completely automatic. And in fact, some of them are even zero-shot, meaning they haven't been trained for this specific collection, or using BERT type or transformer type language. They haven't been fine-tuned for this collection. So hopefully this gives you, some empirical motivation for why we should care about neural approaches to information retrieval. And I would like to stop and think a bit about this zero-shot comment. So these models are, of course, applied zero-shot to the domain, as I said, so they're trained somewhere else, and then they're applied to this collection. This collection happens to be using news documents. So they're news documents, I believe, from the 90s. They're fairly old. They're fairly different from the previous slide I showed you. I'll give you some examples of these later in this introduction section, but they're fairly different from this previous slide, which was web documents and natural language queries, whereas here we're looking at these news documents. And that's zero-shot in the sense of the model. But IR itself, or ad hoc retrieval itself, could also be viewed as zero-shot in the sense that every time we perform ad hoc retrieval, or many times when we perform ad hoc retrieval, we're using a query that we haven't seen before. So for example, you could make up a random string of characters. This is not so interesting, but it's a totally new query. You could, for example, take an error message you see from a piece of code that has a line number. This very easily could become unique. This could be a query that no system has ever seen before. So it's zero-shot in this sense. The task is zero-shot in this sense. We're always confronted with queries we haven't seen before, and we need to determine which documents are relevant to that totally new query. So personally, I think IR is very interesting for this reason. It's an ad hoc retrieval specifically. Ad hoc retrieval specifically is a task where we can never classify things that we've seen before. We always have to think about and deal with totally new queries and how we can handle these arbitrary new queries that come in. And if the query can be interpreted in any meaningful way, we should be able to handle it. So if tomorrow some new iPhone products are released, maybe the name is totally changed, we still expect search engines to be able to find pages that talk about them, even though we know for a fact that the first person issuing that query is issuing a totally new query. As you get into the industry considerations, of course, in industry and Google, there's attention paid to common queries and so on. Not every query is zero-shot, but the core part to me of ad hoc retrieval is that we have to be able to handle these queries that are just totally new. And this is something that is really hard to handle. And I think you'll see, maybe you'll be able to see why some of the methods we use have to be flexible. And rather than specialized to a specific class, for example, they have to work with any sort of terms. I think this will become a bit more clear later as we see examples. Very briefly, Google and Bing have both started using neural methods for retrieval. Of course, they don't tell you exactly what they're doing. I'm not going to read these quotes to you. But the point is that this is now very common. It's clear that neural methods have greatly improved effectiveness for information retrieval. And even though search engines don't want to describe exactly what they're doing because this is bad for spammers and SEO, we have an adversarial situation. Even though they don't describe exactly what they're doing, they will say we use some sort of transformer-based method even. So neural methods and also fairly recent ones at this. So hopefully this has given you some motivation for why neural IR specifically. Now we need to step back a bit and talk about prior approaches, so these unsupervised ranking methods, to understand a little bit better how the neural approaches work and how we like to design them. And we also need, after that, we'll talk a bit about evaluation and data sets, so we can start thinking about what works well and what doesn't, and evaluating things empirically. So as I mentioned, ad hoc retrieval deals with these zero-shot queries, and so evaluation is really a big part of all of this, because we have to just empirically see how well things work often. And including, evaluation is how these unsupervised ranking methods were, how we decide which unsupervised ranking method is good. You'll see that they're not necessarily very obvious. So to start with, when I talk about an unsupervised ranking method, we have some scoring function. So this takes a query and a document as input here. And then it computes a term score. So some function of each term that occurs in both the query and the document. If a term doesn't occur in both the query and document, in this setting, we ignore it. This is, as I mentioned, one of the advantages of neural approaches, that we no longer have to ignore these terms. So as I mentioned in the previous handcrafting slides, some terms are more discriminative. So things like the, and but are not so discriminative. They appear in probably most English language documents or web pages, but they're not necessarily useful terms when you see them. Whereas on the other hand, we have terms like ranking, neural, UFA. These of course don't appear on most documents or say web pages on the internet, but they are, so they're much more discriminative when we see them. And kind of the converse of this is term frequency. So inverse document frequency is a collection statistic. So it's kind of how many documents does the appear in or does UFA appear in, whereas term frequency is a property of a document. So for any given document, we'd expect the, and but to occur much more than these terms on the right, even if the document turns out to be about these terms on the right. So for example, maybe you're looking at a web page about this neural IR module, all of these terms will appear, but it's still likely that these will appear more. And so unsupervised ranking methods tend to balance these two quantities. So the idea is to score a document highly if it contains, some of these discriminative terms, and the more of these discriminative terms it contains, the better. And when I say contain these terms, I'm talking about contains some of these terms from the query. As you remember from the previous slide, we ignore terms that don't appear in both the query and the document. One brief thing I should mention, I'm using document. This is standard terminology in IR, but a document can be anything. So a document can be a web page, a document can be, part of a Wikipedia article, a document can be an entire Wikipedia article, a document can be a book. A document is just the unit of retrieval. So in IR, we always talk about retrieving a document. And so a document is, whatever our unit is that we're returning back. If you're, doing some sort of search at the library, your unit of retrieval is probably a book. Typically with Google, your unit of retrieval, so your documents are things like single web pages. But you can imagine, other scenarios where they're even smaller. If, for example, you're talking to your conversational assistant, a document or the unit of retrieval is probably a passage. You might say something like, hey, Google, how long does so-and-so last in the refrigerator? And then it may read back to you a short paragraph about this. So this would have retrieved a document, which is that paragraph, as a response to your query. So as I mentioned, with unsupervised ranking methods, we're always looking at the intersection of query and document terms. And as we saw briefly in the previous handcrafting slides, this is usually some combination of TF and IDF. Term frequency, how much a term occurs in a document, and IDF, how often the term occurs in a corpus. There's actually an implicit D here that perhaps should be shown. And we'll see that in the next slide when we make things more concrete with what's called the BM25 scoring function, also called a ranking method, for example. BM25, I believe, stands for best match 25. In the lower left-hand quarter, I believe this is a BM25 gas detector, no relation to the ranking method as far as I know. And you see the formula is somewhat complicated, but there's clearly an IDF component here on the left. So N is the number of documents in the corpus. DF is the document frequency of a term, so how many documents that term occurs in. And then on the right, we have this term frequency component. So this is TF on the right, IDF on the left. You see how this reduces to the previous slide if we make functions out of these. But you also, I hope, see how fairly complicated and handcrafted this is. There's a reason it's BM25 and not BM1. This took some time to come up with. Empirically, we know that this works well. So BM25 is one of the, I would say it's the go-to unsupervised ranking method. It works quite well empirically, but it's not so straightforward. And it has these two other parameters, K1 and B. So K1 controls term saturation. Basically, I believe this right-hand side can be no bigger than K1 plus 1, if I'm remembering correctly. Actually, this may depend on the values of B, but the intuition for term saturation is that at some point, we've seen a term in a document so many times that we just say enough. It's no longer interesting to see this term more times. So you could imagine if you see a query term Andromeda 10 times in a document, maybe that should increase the score a bit from 9 times. But at some point, you go from 1,000 occurrences to 1,001, and this term has already appeared so many times that seeing it more is not so helpful, and maybe the score shouldn't increase much of it, if at all. So K1 controls this behavior. B on the right controls length normalization. So the idea here is that we need some normalization of term frequency by the document length, but it's probably not totally fair to just divide the term frequency, so the number of times we see a term, by the raw document length, because what's going to happen here is we're going to really heavily penalize long documents. On the other hand, we do want to penalize long documents somewhat. If, for example, you imagine a single Wikipedia article on the Andromeda galaxy that's relevant to your query, and then you imagine concatenating all of Wikipedia together, maybe excluding any other page that talks about Andromeda or galaxies. We clearly prefer the shorter of these two, and so we do need to do some normalization, but we don't want to normalize so strongly that short documents kind of begin to take over the ranking. And you see, I think, how ad hoc this is. These quantities on the right is the length of a document, and I believe the average length of a document in the collection is the big L. So all of this to say that BM25 is an unsupervised ranking method. It works well, but we can do better, right? So there's clear limitations. It's clearly this is fairly handcrafted. Maybe using only term frequency and IDF we could do better. I don't know. But because we're using neural IR, we know, or neural methods in general, it's likely we can do some sort of representation learning to do better. And this is actually what we're going to do in the context of neural IR. So before we get into that, in the next section, improving representations, I want to talk briefly about evaluation. So we'll go over some metrics and some data sets. So I think it's clear, many people have experience with search engines, or I think everyone here has an experience with a search engine. So we can't use standard metrics like accuracy because the accuracy, for example, would be dominated by false negatives. For any given query, most everything we know about is not relevant, and so this true negative count is always going to dominate. So in IR, we don't worry so much about true negatives. We focus usually on true positives, and false negatives. So precision here will be the number of relevant documents returned over all documents returned. So this is something like true positives over true positives plus false positive. Positive here means that a document is returned in response to a query. This precision is not bad, but typically we would do precision at K, meaning precision at some position in the ranked list, because again, with ad hoc retrieval or with many IR tasks, we know that it doesn't really make sense to go through all the results. Consider, for example, how often you move past the first result page of Google. So precision at K, so for example, precision at 10 would be we look at the top 10 documents returned from that longer list, and out of those 10, we calculate precision. So if, for example, 5 out of the 10 were relevant, then we would say our precision at 10 is 0.5. We also have recall. Recall is the number of relevant documents returned as before, and then in the denominator, it's the total number of relevant documents that exist in the collection. So this metric will be maximized when we find everything possible that's relevant. you can maybe see that this metric is a little bit odd in the sense that it's hard to know everything that is relevant. So typically this is estimated in some way based on some procedures for deciding what sort of document should be judged, pooling the results from various systems and so on. But I think this is more of a topic for the IR1 course. In fact, it was a major topic in the IR1 course, so we're not going to go into much detail on that here. Average precision is essentially the precision at K or at I written here every time a relevant document is returned. So the numerator is the sum of precision at K every time we see a relevant document. So if in position 2 we see a relevant document, we add 0.5 to the numerator. This is relevant document 1, documents returned 2, 1 over 2, 0.5. And then we see our next relevant document, say, at position 5. So now we have 2 relevant documents, and we're at position 5. So this would be adding 2 over 5, or 0.4, to the numerator. So it's the precision whenever a relevant document is returned. And at the bottom is, again, the number of relevant documents in a collection. If you don't follow that closely, it's not so important to know the exact formula, but what is useful to know for looking at results for these methods is the intuition, which is essentially that this metric, average precision, will be maximized when all relevant documents appear above all non-relevant documents. Whereas, for example, precision at K doesn't really care about the ordering. So within those K documents, we can move the relevant documents around wherever we want without affecting the ranking. Which is not ideal. So ideally, we want to put relevant documents above the non-relevant ones, of course. Reciprocal rank is what I showed you earlier when we looked at those MS marker results. This is kind of a special case where we assume there's only one relevant document for a query, and then this is just 1 over the rank of that relevant document. We can also have graded relevance judgments rather than binary relevance judgments. So here in the previous slides, of course, the way we know a document is relevant is through a relevance judgment. So someone has judged that document specifically for the query. And these metrics have been looking at those relevance documents as binary, but this can also be graded. So for example, we have 0 and 1, maybe 0 is non-relevant, 1 could be maybe related, and then say 2 could be highly relevant. So we also have some metrics that can consume this sort of graded judgment rather than only looking at the binary 0 and 1 case as average precision recall would. NDCG is probably the most common of these metrics, and this is what is often going to be reported in results I'll show you later in the lecture. So first, the intuition of DCG, which stands for discounted cumulative gain, is the idea that the higher up is the same as average precision. The higher up relevant documents are, the better, and we should essentially sort documents by their score. So if our relevance grades are 0, 1, and 2, we should place all grade 2 documents above all grade 1 documents above all grade 0 documents. And if we do this, then the NDCG will be 1.0. The N stands for normalized, and we need some sort of normalization. To get this 0 to 1 behavior. So to explain that, let's take a look a bit at the formula. So the numerator is basically asking how relevant a document is. So this particular formulation is 2 to the relevance grade, so 2 to the second power, 2 to the first power, looking at the grades we've seen before. And then the denominator is asking how early the document appeared in the ranked list. So the value of this is decreasing quickly as you're moving down this ranked list, and it's decreasing more than average precision. So in addition to accepting or to using these graded relevance judgments, discounted cumulative gain, DCG, also has the property that it decays more quickly with typical formulations than average precision would. And then, as I said, we need to normalize this. You can see that this quantity is not necessarily going to be between 0 and 1. So we normalize the DCG, discounted cumulative gain, by dividing it by the ideal DCG, which is just sorting all the documents we know about by relevance. So all the 2s, all the 1s, all the 0s, whatever score this list gives us is the ideal DCG. And now, normalizing by that, we have a metric between 0 and 1. So I briefly explained these relevance metrics. I'd also like to briefly talk about test collections. This is especially important for neural IR because we always need, some kind of training data. Even if we're going to train a model in one domain and apply it to another domain, we still need some of that training data to begin with. So a collection, typically in IR called a test collection, this is the same as, say, a data set or a benchmark collection, consists of some queries, some documents, and some relevance judgments for some subset of those documents. So as you can imagine, it's an impossible task to judge every document for every query. If we think about, a typical test collection used, maybe 20 years ago, there's probably, 500,000, maybe more documents in it. It's typical to consider at least 50 queries. So, even 50 times 500,000 is already just obviously far too many, about 25 million, I think, pairs of documents to judge. So only some subset of these documents will be judged. And documents that are not judged are just treated as non-relevant under the assumption that most of what exists is always non-relevant. This is, again, more of a topic for an IR course, but you can see, I think, that if you were to make the assumption that the documents are relevant, this would heavily bias things, and just throwing away the documents also creates some bias. So the safest thing to do is to treat them as non-relevant. But that said, test collections consist of these three things: queries, typically 50, 250, now with neural methods, maybe thousands, documents, and then judgments of whether certain documents are relevant or not to a certain query. So the most common test collection here, and the one we're really going to focus on, is the MS Marco test collection. So this test collection is from the web. It's from Microsoft, that's the MS. Marco is something about reading comprehension. It was originally a data set used for a reading comprehension task, and eventually it was modified, extended into a ranking data set. So the documents are from the web. The queries are questions, so they're natural language questions. Some of them about very popular entities and are somewhat formulaic. So for example, what is the net worth of Bill Gates? I think is a more formulaic one. We have this common entity and we have this kind of template query, what is the net worth of X? But there's also, maybe more interesting, more unusual queries that occur many fewer times, I would expect. So for example, one I recall is, did prohibition increase crime? So this is referring to some historical event in the United States, and the answer is not so straightforward. There's both a passage collection and a document collection. The passages are single passages or paragraphs from web pages using some sort of proprietary segmentation. And then the document collection is the entire web page. A thing to note here is the judgments are sparse. So what this means is for every query, there's only a single document marked relevant, and we assume that every other document is not relevant. Here are some examples of queries. So for example, definition of declaratory judgment. This is kind of a formulaic definition query. How many sons Robert Kraft has? You can see this is a somewhat formulaic entity query. Here's something a bit, less easy to fit into some specific formula. When did rock and roll begin? And then again, something like who is Thomas M. Cooley, a more formulaic query about an entity. Now, you might be wondering how we can have much confidence in this, given that the judgments are sparse. Again, sparse means that each query, so each one of these queries has only a single document marked as relevant. It's pretty obvious, even just looking at the first one, there's more than one dictionary, website on the internet. So clearly there's going to be more than one document that's relevant to this. And the answer is basically twofold. First, empirically, it seems like an okay approximation, but maybe in a more satisfyingly, we have these extended deep learning collections that have the same passages and documents, some of the same queries actually, but for a subset of these queries, so typically 50 per year of this deep learning shared task, there are dense judgments produced by annotators for the query. So for example, they would take this query, who is Thomas M. Cooley, and then they would annotate a large number of documents for relevance to it to try to go much deeper and to address this limitation of having sparse judgments. So often we'll see results reported on both of these collections, but just empirically comparing model performance on MS Marco and deep learning, it seems like evaluating on MS Marco is a reasonable thing. I personally might not trust so much the difference between the best method according to MS Marco and the second best, but the difference between the top method and the 50th method is probably significant. And this is based on other studies and analysis of deep learning results on the deep learning data sets, which is again I think something that I don't want to go into so much in this lecture. We'll focus more on the deep learning aspects. Just trying to give you enough background to kind of process the papers and understand how evaluation works here, because I think as you're seeing, IR is very, very empirical.
The one other test collection I like to talk about is called TREC Robusto 4. TREC refers to a shared task or evaluation forum that created the collection. TREC has been ongoing for a long time, helping us create IR test collections. It's essentially some sort of cooperative competition. Co-opetition, I think they have said at some point, where people submit the results of various systems with known queries and a given document collection, but no relevance judgments. And then this process essentially helps identify what documents should be judged for relevance. So it stands for a text retrieval conference. So Robusto 4 is one test collection from this text retrieval conference. It's a commonly used test collection, partly because it's fairly old, but also partly because it's very thoroughly judged. So you'll remember I said MS Marco has sparse judgments, meaning only one document judged as relevant per query, and we just assume everything else is non-relevant. Whereas with Robusto 4, it's very deeply judged. Not completely. It has about 500,000 documents and 250 queries, so judging all of these would still be a lot, judging all possible pairs. But it's very thoroughly judged. And so this collection consists of news documents, I believe from the mid to early 90s, definitely before the year 2000. Keyword queries, so these are also called title queries sometimes. So for example, Black Bear attacks is an example of a keyword query. This is query ID 336. And then also these natural language description queries. So here, the same information need as Black Bear attacks is expressed in this description query. So a relevant document would discuss the frequency of vicious black bear attacks worldwide and the possible causes for this savage behavior. It also contains a narrative, which is essentially just a much more detailed description of what makes a document relevant. I believe these were written by the annotators or assessors as they were judging documents, but they're typically not used as queries. One thing to just note is that these description queries, though they are natural language, are a bit different than the natural language queries we saw, here with MS Marco. So these are, really brief web-style natural language questions as queries, where these description queries are really more like natural language descriptions of what kinds of documents would be relevant to a given information need. So that brings us to the re-ranking section. Here, I'd like to talk a little bit about what a re-ranking pipeline is, how we represent queries and documents in this world of neural IR, where we're using neural machinery to perform ad hoc retrieval. And then we'll essentially make this more sophisticated as we go. So we'll start with some basic or bag of words approaches for representing queries and documents and for re-ranking them. And then we'll move to more modern approaches where we use contextualized representations and we use transformers. For example, BERT, if you've heard of this method before for re-ranking. But before we get into all of that, I need to explain a bit what re-ranking actually means. So here we have a simple search engine. In this slide, we're showing a re-ranking, or I'm showing a re-ranking pipeline. So there are some texts or documents that are stored in an inverted index. A bit more about that in a second. And then using this inverted index, an efficient unsupervised method like BM25 can receive a query and identify some documents that appear relevant to the query, based on, for example, BM25 scoring. And the idea of re-ranking is we might take some of these documents that were returned by BM25, so maybe the top 100, or let's say the top 1,000 documents returned by BM25, and re-rank or reorder them with some sort of neural method. So the idea here is that out of these, say, 1,000 documents, it's really unlikely that the user is going to read through all of them, It's really rare to go to, what is this, the 50th result page of Google, assuming it shows 20 results per page. I don't even know if this is relevant, if this is correct. But you generally don't look at 1,000 results for, say, web search or many common ad hoc retrieval tasks. So the idea here is we can take those 1,000 and then we can reorder them, shuffle them around based on their relevance according to this neural, more accurate or more effective method. And then hopefully we'll find the most relevant documents from those 1,000 and move them to the top of the list. So ideally, to satisfy the user's information need, rather than going through all 1,000, they can only look at, say, the top documents in this list, and these top documents will be much higher quality than the initial documents that were retrieved by BM25. So, just to make this really concrete, maybe BM25 returns relevant documents at positions 100 and 200. With a good neural ranking method or re-ranking method, we would hope that these documents, which were previously at positions 100 and 200, would move up to positions 1 and 2, or at least this is the idea. And so this gives us a final re-ranked result list. So often when we evaluate this sort of re-ranking method, what we'll do is we'll compute some metric for the first stage retrieval method or the initial retrieval method like BM25. And we'll say something like BM25 has an MRR of 0.18. This is close but not exactly to what I showed you in that previous MS Marco slide. And then with the re-ranker, we'll say, well, after re-ranking these documents, our MRR, mean reciprocal rank, went up from, say, 0.18 to, I don't know, maybe 0.33. This is close again, but not exactly to what was shown on that MS Marco slide. We'll see empirically that this is an effective way to do things, but these re-rankers aren't so efficient. Now, the reason they're not efficient has to do with what this inverted index is, which I kind of glossed over. If you've taken an IR class before, I think you already know what this is, but just a brief refresher. An inverted index is essentially an efficient data structure that's efficient for retrieval, where for each term we store a list of documents that contain that term, and then maybe some type of score for the document. So you can imagine that BM25 quantity on the right might be stored for each time a term appears, or for each document a term appears in. So for example, we might have the term Andromeda, and then what's called a posting list associated with that term that says Andromeda appears in document 1 with score 5, and it appears in document 7 with score 2, and so on and so on. And then you can see, I think, by how using these lists, you can quickly compute a score for all the query terms, because there's no sort of soft matching. We know exactly which lists we need to look at. We need to look at one list for every term in the query. So you can see, I think, how this can be done very efficiently for something like BM25, where we can pre-compute all these scores and then store them in an inverted index. However, it's not so clear at this point how we could do this efficiently with neural methods. So one way neural methods are used is simply as re-ranking methods, where they take, say, all 100 or 1,000 of the candidate text as input, and they compute a new score for those 1,000. And this might not be so fast for each document, but because we're only computing the score for 1,000 documents, it can still be reasonably efficient. Later, in the second lecture, part 2 of the neural IR model, we'll look at how this can be sped up. The very short answer is that there's this approximate nearest neighbor data structure that can be used to kind of find the nearest neighbors of a vector representing the query, and so this can also be done efficiently. But this is getting a bit ahead of things. In this lecture, we're going to be talking about re-rankers. And so, as I said, this re-ranking pipeline we'll be considering in this section. So we'll have some initial retrieval method like BM25 that provides candidate documents. And then the models we're talking about will be re-ranking those candidate documents, so producing a new score for those candidate documents, so we end up with a higher quality ranked list. So this brings us to query and document representations. Where this will be broken down into basic query and document representations. Another word for this is static or bag of words representations. You'll see why in a second. And then after looking at this approach, we'll look at a slightly more modern approach where the representations are contextualized. So static word embeddings are essentially meaningful vector representations of words. I think you've probably heard of methods like glove, word2vec, fast text before. These are essentially self-supervised methods for creating word embeddings, and an embedding is a vector representation of a word. So you can see that, and here's some example figures that are commonly used from this website. So you can see that these vectors have some kind of useful properties. So for example, terms about people like king and man, king and woman, king and queen, queen and man, etc., are all somewhat nearby and have some similarity in the embedding space. You would imagine, for example, say king and queen to be more similar to one another than, for example, I don't know, king and ant, like the animal ant, not the person ant. But of course, the similar types of similarities here are not defined in advance. This is just learned through some self-supervised prediction task. Essentially, the task is given a word, predict which words are nearby, and then update these vector embeddings of each word as this happens. Continuously do this over a lot of documents, a large corpus, and eventually, the vector representations are meaningful. So because there's no type of similarity pre-specified in advance, these capture a lot of things. So for example, verb tenses, walking is similar to walked in some sense, or even country and capital. So Spain has some similarity to Madrid, and the similarity of Spain to Madrid should be higher or is likely higher than the similarity of, say, Spain to Rome. When I say similarity here, I'm typically talking about cosine similarity, but this could also be a dot product. This depends on the specifics of the method, or of the method using the word embeddings. But a really common way to use word embeddings is to take the cosine similarity between them. And what we do in the case of neural IR is we often build some sort of similarity matrix, or at least with static word embeddings, a similarity matrix is often used. Even in more modern methods, there's often a similarity matrix inside, but it's not necessarily called this. Another word for similarity matrix is, say, a translation matrix or a matching matrix. But what is a similarity matrix? So here in the rows, we see query, green sea turtle, and then in the columns, we see some snippet from a document. So reptiles such as sea turtles spend most of ... Each cell here indicates the cosine similarity, in this example, cosine similarity, between a query term and a document term. So for example, we can see that the term C has a similarity of 1.0 with itself. This is because the word embeddings are static, or they're bag of words embeddings, meaning regardless of the context, they're always the same. So of course, the vector always has a cosine similarity of 1 with itself because it's the same vector. However, if we look at similarity between different terms, we can see, for example, the similarity between sea and turtles is non-zero. No exact value given here, but there's some non-zero similarity. We can see that we have something similar if we look at, say, turtle and turtles. So these are not exactly the same term. They're actually different vectors because they're different terms, turtles singular and turtles plural. But they have a high similarity, probably close to 1, probably 0.8, probably 0.9. This is just an example. I'm not sure of what the exact value would be. We'd have to nail down a lot of specifics about, for example, whether we're talking about word2vec or glove. If we're talking about word2vec, what is the size of these vectors, or the dimension of the vectors? Is it trained with this variant or that variant, and so on? But the point being, this similarity matrix is a way to measure the similarity between query and document terms. Many neural retrieval methods have something like a similarity matrix inside, even if it's not called that. So this similarity matrix is essentially a basic type of representation for queries and documents. I say basic because terms are static, or you could also say bag of words. So this kind of raises the question of how we can use these matrices. So next we move to bag of words re-ranking. So my favorite method to talk about here, one that I think is really nice, that it works well, I like the motivation, I like that it's end-to-end differentiable, is CANRM. This is from the paper End-to-End Neural Ad Hoc Ranking with Kernel Pooling. It stands for something like a kernel neural relevance model, kernel pooling. But the idea is that first we create some similarity matrix. In the paper, they call this a translation matrix. And then given the similarity matrix, it's going to create something like a differentiable histogram or a soft histogram. So basically, we're going to count, given this query term C, how many document terms are around 1.0 similarity? How many document terms are around 0.9 similarity? How many are around 0.8 similarity? This sort of thing. And this they call kernel pooling. And you can see that this is extending the matching machinery to soft matches. With BM25, we were only looking at exact matches, so we would never add something to the score unless the terms matched exactly. Whereas here, we have some opportunity to do so because we're using these static embeddings. So the way this works is first we create that similarity matrix we saw on the previous slide. Next, we apply these Gaussian kernels to each row, meaning to each query term. So we have some similarity term in the cell, and then we have some mu, which is a hyperparameter. In practice, there's a few of these with different mu's. So for example, we have a mu for 0.9 to count how many similarities are around 0.9. We'll have a separate one for 0.8, and so on. We also have this sigma hyperparameter, and of course this is set, it's essentially the width of the soft histogram. So we want it to be large enough to capture things around 0.9, but not so large that, say, 0.8 contributes a lot, because our plan is to also have a separate mu for 0.8. So after we've applied these Gaussian kernels, we have these k different kernel scores, and we're going to sum them across different terms. So for example, we're going to take the log of k1. So this is, remember that k, if we go back a bit, is this mu. So we have k different mu's and sigmas. So this is k sub k, a little confusing, I suppose. And so for the first one, say this is 1.0, we're going to take the log of this and sum it across all the query terms, and do this for each of the buckets, so to speak, so each of these differentiable histograms. This gives us so this vector, this phi of m, because this is the sum of these across query terms, so we're still left with a vector of size k. And we essentially just use a feed-forward network, or you could call it a fully connected layer, a dense layer, whatever terminology you use, to compute a score given that vector. So basically, to throw away the differentiable part of this, just to talk about it at a high level, what's happening is we're creating some vector. Say we want 10 bins in our histogram, so then it would be a vector of dimension 10, and each position in this vector is going to indicate how many good matches there were between a query and a document term at that similarity level. So if we take the bin around 1.0, well, how many times did the terms match exactly? 0.9 is a non-exact but high match. So we saw that a bit in the similarity matrix. I'll go way back just to give you an illustration. So for example, maybe turtle and turtles fits in the 0.9 bin. Maybe C and C fits in the 1.0 bin, for example. Maybe turtle versus of is a 0.1, say, bin, for example. So we're creating this vector, essentially this k scores corresponding to these k bins. And then we're using a feed-forward network to compute a score for the document given that vector. Now, the point of the Gaussian kernels is essentially this is all differentiable. There's another method called a deep DRMM, the Deep Relevance Matching Model, I believe, published the year before by some authors at UMass and the UCAS. Guo and Croft are the first and last author. But this canner M builds a bit upon it, and then it's differentiable. And so typically, the embeddings used are trained along with the model. So it's kind of an end-to-end. You can initialize it with some embeddings, but they can also be updated as you train. And in this way, you can score documents using these static embeddings. So I call it a bag of words approach because it's using these static embeddings, and there's nothing about the method itself that's taking into consideration positions of terms within the query or the document. You can imagine other approaches that do so. So for example, you can imagine using a 2D CNN over that similarity matrix to capture patterns, for example. This is one method of Packer by Kai Hui from my previous institution and I and some other authors. There's all sorts of ways you can consume the similarity matrix to try to make it non-bag of words. But really, in order to really improve things, we need to make things a bit more complicated and look at contextualized embeddings. So the key thing I would say holding this method back is that the embeddings are static. So no matter the context of a word, we always represent it in the same way. So that brings us to these contextualized query and document representations, where contextualized means, given a term, the term if we say the sun rises, the embedding for sun is different than if we say the sun also rises, which is the name of a book by Hemingway. So we have two different inputs, so we have two different embeddings for that term. They're fully contextualized based on the entire input. And now in this section, I'll give you an example of, or I'll walk through how this is done. So as I said, the idea is that word representation should vary with context. And so rather than having a one-to-one mapping between term and some static embedding, we instead generate embeddings given the full context of the word. So given a full sentence or a full document, we now generate an embedding for every term in that sentence or document. Whereas Word2Vec have one embedding per word, and then they're based on basically looking at co-occurrences of word pairs. So say pet dog versus pet taxes. Pet dog is much more likely. The embeddings for those terms should be much more similar. The canonical approach to contextualized embeddings is BERT. So this is what I'm going to go through as an example. This may not be new at all to some of you. I'll talk also about the IR connections for this. But after we go through BERT, we're going to start getting into the very IR specific part of this neural machinery, where we look at how BERT can be used for re-ranking. So on the right, we see a transformer encoder layer. I think the top text that says transformer encoder is cut off, but that's okay. Nothing much is missing other than that. And fortunately, in the Deep Learning 2 course website, we have a really nice tutorial under DL1 tutorial 6 talking about these transformer layers. So rather than trying to explain these to you in a lot of detail, I would refer you to this tutorial. The intuition here is that essentially you're taking the transformer encoder, takes a long sequence as input, and then uses some sort of self-attention to compare all other terms in that input and essentially rewrite the terms. We'll go through, you'll see something about how this looks with BERT. So first we start with the string, so something like the bank makes loans to clients. First, this is converted to tokens. With BERT, there's a convention to prepend the CLS token and add to the end the separator token. And so now we have the bank makes loans to clients with the period separated and these tokens added. BERT has some static embeddings at the input layer. So these are the token embeddings. It also adds some other types of embeddings to these token embeddings. So it also has this notion of segment embeddings. Each term or each input can be either a part of segment A or segment B. This is just related to how BERT was pre-trained. I suppose more could be created. And in fact, there is work in IR creating, for example, a third one. And there's position embeddings. So there's nothing about a transformer encoder layer that considers position inside the layer, or at least inside the typical one. There are modifications that do so, but inside the original canonical transformer encoder layer, there's nothing that considers position. And so there's also some sort of position embedding added. So this is just saying that this term is at position 0, this term is at position 1, this term is at position 2, and so on. And so this will allow the transformer to essentially identify what terms are nearby. So you can see by comparing the embeddings that the is closer to CLS, the special token, than it is to clients, because position 1 should be closer to 0 than it is to 6. And so the input to BERT is just the summation of these three embeddings. So the token embedding for each term, the segment embedding indicating if it's segment A or segment B, and the position embedding. Later, in a few slides, we'll see that for re-ranking, we typically use these segment embeddings to denote a query in a document. So we're going to do something like insert the query as an input with segment A and the document and each document with segment B separately, and then compute scores for all these pairs. So you can see why I said this is not so efficient. Given these input embeddings, so the summation of these, we now have this BERT, which is a series of transformer layers. So BERT base, which is typically the most commonly used BERT variant, consists of 12 transformer layers. It has a vector size of 768. I believe the hidden size in this transformer encoder is 2048. It might be 3072 though. I believe it's 2048, not so important though. The key thing to know is there's 12 of these layers stacked together, and then each embedding is 768 dimensions. So you already see these embeddings will be a bit bigger than what we typically use with Word2Vec, which is often, or was often, 300 dimensions. So given we sum these together, this forms the input to BERT. This is processed with the stack of the transformer encoder layers, and then it creates an output for every input position. So this is why it's a transformer encoder, because for every input we have a corresponding output. For a decoder, we could have in inputs and im outputs, whereas here we always have in inputs and in outputs. So essentially, what we get out here are contextualized embeddings. So here we would have had a static embedding for bank, regardless of whether the sentence was the bank makes loans to clients, or I'm sitting on the bank by a river, or how do you bank a plane, as in turn a plane. But what we'll get out should be very different for these three inputs. The embedding for bank should and does generally reflect the sense of it. So we would have a very different bank in this example when it's talking about finance versus sitting on the bank talking more about landscape, something outdoors. The key thing to know here though is that we have some embeddings as input. We use BERT, which is the stack of transformer layers that's pre-trained, to rewrite or to encode the embeddings to contextualize them, so to speak. So I haven't explained yet exactly where these layers come from. Why is it called BERT rather than just 12 transformer layers? Well, there's some pre-training of these layers using self-supervised tasks, similar to Word2Vec. So here, as before, we have some input, but what I've done is I've replaced the word to here with this special mask token to illustrate the pre-training task. And so in this task, what will happen is random parts of the input will be masked or hidden. So here we've masked 2, and then we'll try to the model will try to predict the correct term corresponding to this masked position. So here the objective would be to maximize or to minimize this quantity. So to minimize the negative log likelihood. So because 2 is the correct answer here. So similar to Word2Vec, this is done using a lot of compute, more compute than Word2Vec, a lot of documents, a lot of text, and then after the self-supervised pre-training is complete, we have some transformer layers here that are initialized in a way that they can be applied to other tasks. So this was just a quick description of BERT. Hopefully you've seen BERT before. If not, I think this is enough for our purposes. But either way, I'd recommend diving into this lecture. This tutorial, I mentioned the deep learning tutorial number 6, which is also on the website. This will go into a lot more detail about exactly what's inside these transformer encoder layers. Transformer decoder layers are also relevant, but we won't see them as much in IR. We'll have one example this lecture using a transformer decoder. The thing to know there is essentially we're producing some output, so it's a sequence-to-sequence model rather than an encoder. So that brings us to how we can use these transformer or BERT-based methods for re-ranking. If you remember the motivation slides I showed you earlier, where we saw, on Robusto 4, we've seen very recent improvements in effectiveness. Similarly, on MS Marco, we've also seen really big improvements. Google and Bing said they've seen very big improvements. These are all due to transformer-based methods. So while KNRM is a really great method, it's somewhat limited by the fact that it's using these static embeddings. And we'll actually see that applying it, coupling it with a transformer can improve it and perform quite well. But first, how do we perform re-ranking with BERT or with other transformer-based methods? So here, what we want to do is compute the probability of relevance given a query and a specific document. So earlier, I was talking about how IR, the task itself, is kind of zero shot, and that we often have a query we've never seen before. This is hopefully is clear from this formulation. So we're always predicting the probability of relevance, but it's relevance given totally different queries and totally different documents. So the relevant class doesn't say much in itself. There's nothing we could really do to learn a relevance classifier independent of any query and document. I suppose this would just be something like a spam classifier at best, where we can say some things look like nonsense, but otherwise it's unclear if they're relevant or not. So we want to compute this quantity, probability of relevance given a query and a document. To do that, we can make use of these two segment embeddings, as I hinted at earlier. So this is the monobert approach by Nogueira and Cho, published Archive 2019, passage re-ranking with BERT. Essentially what we do is we input query Q. This is segment A, so this is input 1. And we input one document D sub I. This is segment B. So you see we'll need to do this for every document that we want to re-rank for the query. So given a query and 1,000 documents to be re-ranked, we now have to run BERT, so to speak, 1,000 times. So we input both of these. We have this transformer compute some outputs. Rather than using the contextualized embeddings directly, Rodrigo makes use of this CLS token. In the BERT paper, this was proposed as a way to do classification. So by convention, the first token, as I mentioned, is always CLS. And then this can be used as kind of a summary or a task summary token, kind of. So the idea is we take whatever vector we have here, we run it through a feed-forward network, and then we get some score for relevant or non-relevant. In practice, whether there's two classes or one varies, but I think they're more or less equivalent in practice. The one here indicates that we're taking this probability of the relevant class. So we can do this. We'll need to fine-tune the model. So of course, BERT out of the box is not going to compute relevance versus some other similarity, but we can insert some queries. We can insert some documents, and then we can use it with something like a cross-entropy loss. I'll show you an example of that. So here we have some positive documents or relevant documents. These generally come from human annotations, and we have some negative documents. These typically come from the output of a first stage retrieval method. So say we run BM25, we get those 1,000 candidates, and then everything that was not marked relevant becomes a non-relevant or a negative example. So we can use it with a loss like this in a data set like MS Marco to fine-tune, so to speak, the BERT model. Fine-tuning essentially refers to the fact that we're starting from this pre-trained model and just updating it a little bit, at least a little bit in comparison to all the pre-training that's already happened. So here we have some results on MS Marco. Just a quick refresher, you'll recall that MS Marco is this web collection with these natural language question queries, things like what is the net worth of Bill Gates? As I mentioned, often when we compare results, we'll look at the initial re-ranking method, the initial retrieval method, so BM25, and then compare that to BM25 with some re-ranking. So what we see is a pretty good increase in NDCG and average precision. These are two metrics you've seen. Recall at 1,000 stays the same because we're re-ranking all 1,000. So we haven't changed anything about those 1,000. We've already moved them around, which doesn't matter for recall. But we see we have a big increase in NDCG, some close to a 50% improvement, not quite, and also a nice increase for average precision. We can also see that if we change the first stage retrieval method used, So this is BM25 with some query expansion method added on. The details of this are not so important for Deep Learning 2 specifically, but what a query expansion method is going to do is essentially add new terms to the query that are hopefully useful with very specific weights. So we see that this is robust to the different choice of retrieval method. We see similar improvements. RM3 performs a little bit better, but still, with the re-ranking step, NDCG increases, quite significantly, about 0.52 to about 0.74. So we see that there's a very big increase just from taking this, application of BERT and applying it directly as a relevance classifier to re-ranked documents. Now, when we looked at CAN-RM, I was talking about similarity matrices. I mentioned similarity matrices as a basic way for query document representation. Well, we can also use, a pre-BERT method that consumes similarity matrices with these contextualized embeddings. So what we can do is we can essentially create contextualized embeddings with BERT. So we feed the query in, we feed the document in, and then we get some embeddings out, some query embeddings here, some document embeddings here. We construct a similarity matrix from those embeddings. So we've essentially just replaced word2vec with that similarity matrix construction with BERT using its contextualized embeddings for the similarity matrix construction. And then once we have that similarity matrix, we could use something like CAN-RM that I showed you earlier to compute a score given the similarity matrix. So this is essentially a second way to use BERT, taking advantage of those contextualized embeddings rather than treating it as a relevance classifier. This paper has some figures that I think give a nice intuition of why BERT is helping here, why the contextualized embeddings specifically are helping. So I'd like to take a minute to unpack these. So on the left, we have a relevant document. On the right, we have a non-relevant document. In both cases, on the x-axis or on the columns, we have the query, so curbing population growth. It's always the same. And on the rows or the y-axis, we have some snippet from a document. One quick thing to note here is you notice that the tokens are a bit different from GLOVE on the left and BERT on the right. With GLOVE, curbing is one word. With BERT, curbing is two words. This has to do with BERT's tokenization, which I didn't really get into. But BERT essentially uses what's called word piece tokenization, meaning it has a fixed vocabulary. It's something around 33,000 terms. And every time you see a term in a piece of text, either it's already in this vocabulary, in which case you're fine. It's something like population, nothing needs to be done. Or it's not in the vocabulary, but it can be decomposed into different tokens that are in the vocabulary. So here, curbing was not in the vocabulary, and it's decomposed into curb and ing, which both are in the vocabulary. So these end up being treated as separate tokens by BERT. This may seem a bit odd, but this is also how it's pre-trained, and it seems to work well in practice. So anyway, on the left, we have a relevant document. Document here, query text here, as I said. So if we look at the similarity between curb in the document and curbing in the query, it's 0.6 with GLOVE. We look at the non-relevant document, curb in the document, curbing in the query, it's still 0.6, and of course it is because the vectors for curb and curbing have not changed. They're always the same. However, using the contextualized embeddings here, we see the similarity changes. So the similarity between curb and curb for BERT in the relevant document is 0.7. Here, curb is in the sense to slow in both the query and the document. Or if we look in the non-relevant document between, again, curb and curb, the similarity has dropped from 0.7 to 0.5. The reason for that is in the non-relevant document, it's talking about curb construction. So, the raised area by the side of the street, or at least by the side of some streets, versus curb as in the verb to slow. So we see that the contextualized embeddings have reduced the similarity here in the non-relevant document. And so this gives you, some intuition for how these contextualized embeddings are useful. Now we can look at some results from this method, the CEDAR method. So let's mostly compare, I think, to BM25. So BM25, now we're looking at the other dataset, Robusto4 rather than MS Marco. It starts off about 0.414. This could be increased a bit. I think this BM25 run is a little low, but it's never above, I think with BM25 only 0.44. With RM3, it can go a bit higher. Now let's focus on the Cedar CanRM row. This is CanRM, the model we saw earlier. That's why I'm most interested in this row. We see the similarity has improved from mid 0.4s to 0.53 about. So this is, sorry, the metric has improved to 0.53 about. So this is a pretty significant improvement. We haven't talked about these other methods, Packer and DRMM, but the details are not so important. What you need to know is these are other methods for consuming a similarity matrix. So Packer is a method that uses 2D convolutions to essentially look for patterns, so bigrams, trigrams, etc. in the similarity matrix. DRMM is similar to CanRMM, but it's not differentiable. So I briefly mentioned this earlier. DRMM is using just histograms constructed kind of as a pre-processing or input step. Histogram construction is, of course, not differentiable unless you're doing something like the kernel pooling approach of CanRM to create, something like a soft histogram approximation. So we see that with all these pre-BERT methods, however, there's a pretty big improvement over this BM25 unsupervised method. And as you'll recall from earlier, BM25 is really one of the state-of-the-art unsupervised methods. Now, something I didn't mention back here is that in addition to using the similarity matrix, Cedar sometimes also takes that CLS token and concats it with basically at the final layer in one of these models. So you'll remember we had this final feed-forward layer that took the kernel pooling vector and computed a score. So there's Cedar, some variations take that, essentially a vector like that, concat the CLS token to that, and then feed that to a feed-forward network to compute the score. And this is shown in these two rows, 4C versus 4D. So we see there's some improvement. So from concatenating the CLS token versus not. But either way, we have a good improvement over the initial BM25 method. I should also mention that whether or not there's an improvement from concatenating the CLS token really varies on the experimental setup. So here in these experiments, there is some improvement from concatenating it. However, in later reproduction work, it seems that there is not much of an improvement in many cases. So it's really unclear how useful the CLS token is in this context. But the takeaway message is that using these contextualized embeddings does improve a lot over, for example, word2vec. So this gives us evidence that, at least one reason that BERT transformers neural methods are so helpful for IR is that they're improving these static embeddings, going from static to contextualized. I guess finally, we can look at this row 4A. This is just using CanRM with Glove, so similar to word2vec, and you see that it performs much worse. And it's the same with Packer, it's the same with DRMM. So really, the secret sauce here is that BERT model for contextualizing the embeddings. And hopefully that's clear from the last slide where we saw the difference between curb and curbing in a relevant and non-relevant sense. So finally, to wrap up this lecture, I'd like to talk a little bit about how we can improve effectiveness in this setting that we've seen so far. So far, we've been looking at BERT-based primarily. This is a model with about 110 million parameters. It's the standard BERT model I mentioned, 12 transformer layers. But there are also other, transformer methods or BERT variants that improve a little bit over it. So the one I want to talk about here is Electra. So you'll recall that BERT does this random masking. So it randomly replaces a term with mask, and then it tries to predict the mask term. Electra modifies this task to be term replacement. So rather than masking some terms, some terms are replaced with a smaller generative model. And then Electra's task is to predict, based on this embedding that comes out, whether this term is the original or whether it was replaced. So in other words, it's kind of, the task is kind of to predict whether the term fits with the surrounding context or not. Bank fits with the context of loan and clients. Store doesn't so much fit with that context of loan and clients. So the main key point of Electra is it's simply changing this pre-training task from mass language modeling to this term replacement task. And what we see is this actually brings some pretty decent benefits. Out of these various BERT variants listed in this table, I only went through Electra in detail because this is the one where it seems like there is some benefit to using it. Let's go through all of them just to take a quick look. So we're looking at NDCG at 20 on Robusto 4. So this is the same metric that was used for CEDAR. So here we see that, and I should mention this is monobert. So this is using BERT as a relevance classifier rather than CEDAR where we're using contextualized embeddings, which is why these numbers are a bit lower, I suppose. So looking at NDCG at 20, we see that BERT base with pre-training both supervision task and pre-fine tuning on that MS Marco collection is about 0.49, whereas Electra is about 0.52. Now, if we eliminate that pre-fine tuning, so we go up here, so this means BERT is, it's pre-trained as normal, and then it's fine-tuned directly on Robusto 4 without this intermediate fine-tuning step on a larger data set. We see a little bit of a drop. Same thing with Electra, a bit bigger drop though, 0.49 to 0.52. If we look at the other methods, they are a little bit lower than Electra. Albert is significantly worse. Roberta is a bit worse. Roberta with pre-fine tuning does not perform as well as Electra here. All this to say, this seems like a good BERT variant for IR in the sense that it performs a bit better across a few different data sets. And we also see similar results if we switch from these title or keyword queries to the description or natural language queries. Don't want to go into a lot of detail here, but again, pre-fine tuning is better than not pre-fine tuning. So compare, for example, 0.55 to 0.53, 0.57 to 0.55. And we see that Electra, again, is a bit better than BERT base. All this to say, there are many transformer models out there. There can be, very large claims about how much one has improved. This does seem to be the case for many tasks, but whether a transformer model will improve for ranking specifically, it doesn't seem to be that simple. Transformer models, so for example, say Roberta, that seem to be better at some different types of NLP tasks are not necessarily better for ranking. It does seem like Electra is better though. It does seem to have consistent improvements on this data set and others. And so finally, I just want to compare the difference between a keyword query and a natural language query. It's 0.52 versus 0.57. So we see there does seem to be some benefit from moving from keywords to natural language. Another way to put that is that these models seem to be better at consuming natural language queries than they are at consuming keyword queries, or at least they can get more mileage out of them, so to speak. The natural language provides more context, it probably matches the training data better, and it just works a bit better in practice, it seems. One other alternate approach I'd like to talk about is T5. So Electra I called a BERT variant because it was still a stack of transformer encoder layers. T5 is something a bit different because it's a sequence-to-sequence model. In addition to that, it's larger, it has some improved pre-training, but what I want to focus on here is the sequence-to-sequence aspect. So how this works is a sequence-to-sequence model, of course, outputs some text, and it generates some text given an input, essentially. So the input here is query, a query, document, a document, relevant, and then the model's job is to essentially output some text completing that template. So at training time, the model is trained to either output true or false. If it's a relevant document, it's trained to output true. If it's a non-relevant document, it's trained to output false. Pretty straightforward. Then at inference time, the way documents are scored is by computing the probability of outputting the true token. So in this way, T5 can be used as a ranking model. This is also Rodrigo Noguera's work. You see the citation here, document re-ranking with a pre-trained sequence-to-sequence model. And so we can compare this to a BERT model. I don't want to get into the details of exactly how this BERT model works now. I think the most relevant thing to know is that it's based on BERT large. So it's a transformer encoder, not a sequence-to-sequence model, a bit smaller than T5. And it's about the same size as T5 large. T5 large has both encoder and decoder stack. So the encoder stack in T5 large is roughly the same size as the stack in BERT large. And then the overall model size is about twice as big. So about 300 something million, 330 million, 600 something million for T5. And if we look at results on Robusto 4, these are zero-shot results, meaning T5 was not trained or fine-tuned in any way on Robusto 4. We see there's pretty big improvements over this BERT large method. So if we look at Birch, NDCG is about 0.53. That's in line with the NDCGs we've been seeing on this data set so far. Recall that average precision is another metric, and we see similar trends here with that metric. NDCG has just a higher discounting and also uses relevance grades, although relevance grades are not really coming into play much on Robusto 4. So we see that BERT large is about 0.53 NDCG. Smaller T5 is 0.55. That's actually better. Strangely, large T5 is not better. It's a little bit worse. I don't think this is probably it's not a significant difference, but it is a little worse there. But we see when using the larger T5 model, so about an order of magnitude larger than this BERT large model, NDCG increases quite a bit to 0.61. And this 0.61 is actually, as far as I know, one of the state-of-the-art result on this data set. So there's one other method that can achieve around 0.61, but this method is not zero-shot, whereas T5 is zero-shot in the sense that it is not, it's not fine-tuned at all on Robusto 4. I should also mention that these are description queries. So the results would, of course, be lower with keyword queries. The description queries, as we saw in the last slides, are easier for these methods to use. They provide better input. And then finally, just looking at BM25 again quickly, we see 0.44, 0.42, depending on whether we have query expansion or not. I'm really just focusing on the query expansion lines because they perform a bit better. There's not much difference between the two. And both T5 and this Birch method using BERT large are substantially improving over this BM25 with query expansion method being re-ranked. So we see that this T5 approach brought a pretty big significant effectiveness increase. Now it's also, of course, even less efficient than BERT. Whether or not this makes sense for the task is, I think, specific to the task and to the user. As I mentioned, it's an order of magnitude bigger than BERT large. But for that, you do get a big increase in effectiveness, and it even works well zero-shot, and it achieves the state-of-the-art result on this data set. So finally, that brings us to the end of this part, where we looked at re-ranking methods in depth. I showed you re-ranking methods, both with these bag of words, static, basic word embeddings, whichever term you want to use. And we also looked at re-ranking methods that are, a bit more advanced. This is what would be, used more modernly with these contextualized query and document representations. I have to add that when I say more modernly in the context of neural IR, we're talking about like 2007 versus 2019 or 2020. So, of course, these are all very recent methods. But, the methods being used most often today, the active research, is with these transformer-based or BERT-based methods. And so with that, I just want to talk a little bit about the limitations we've seen. So first, remember when we were creating BERT's input, we needed these position embeddings for every possible position. So we have an embedding of what it means to be at position 0. We have an embedding of what it means to be at position 1, and so on. We have all these position embeddings. Well, what this means is that we have some maximum input that we can provide to BERT. Typically, the standard BERT model is trained with 512 position embeddings, meaning we have positions 0 through 511. So, if we have a document with 1,000 tokens, there's just no position embeddings for half of that document, and there's no reasonable way to feed it into BERT. It's just going to, there's nothing reasonable to do. If you tried to, for example, repeat position 512 over and over, you would have some weird mix of a bag of words for the last half of the document and a position-aware representation for the first half. There's no reasonable way to feed that in without learning new position embeddings. So this raises issues of exactly what we input, and if we're inputting parts of documents, how exactly we can label it. So this is one limitation. I would say it's one of the easier of the two limitations to overcome, but I'll very briefly talk about this limitation in part 2. But really what I'm going to focus on in part 2, this is the main point, is the second limitation of efficiency. So I mentioned that these layers are computationally expensive. They have about 110 million learned weights in them. So they're, and we have to feed everything in as a pair. So, if we have 1,000 candidate documents we want to re-rank, we're rerunning BERT 1,000 times, so to speak. Maybe 1,000 times isn't so bad, but it's probably not extremely fast. It's nowhere near as fast as BM25, because this is still, quite a significant method. Maybe with a lot of hardware, it could be made to run fast enough, but even in a re-ranking approach, this is really not efficient. So in this lecture, in this first part, what we've seen is how to address this efficiency problem using a multi-stage ranking pipeline. So identifying candidate documents and then re-ranking only those 1,000. It wouldn't even be possible to use this at all if we had to re-rank every document or to rank every document in the collection. But what we'll look at in the next lecture is how we can address these efficiency limitations. So I think the takeaway for part 1 is that we've seen that no re-rankers have greatly improved effectiveness. We've seen, compared to the state-of-the-art BM25 unsupervised method, really big increases in the metrics across data sets and across query types. But as I just hopefully convinced you of, there are big efficiency problems. In part 2 of the lecture, we're going to look at how we address these efficiency limitations. So we'll look at using, for example, approximate nearest neighbor indices is one approach, where we can encode queries and documents into vectors separately, and then use this efficient approximate nearest neighbor index to ask what are the nearest neighbors of this query vector. And another type of efficient approach, which we'll also look at, is kind of going way back to the beginning, where we're talking about TF-IDF, and rather than changing how we use an inverted index, so to speak, we're going to change what we put inside an inverted index. So these approaches are also pretty interesting, I would say. They're called learned sparse representations. And the idea here is we essentially learn some score that we replace TF-IDF with. So rather than having these two handcrafted scores we multiply together, maybe we have a transformer model, create a score for every term in a document ourselves. And then that score can go directly into an inverted index, and we can use these efficient methods with the inverted index. So these are two families of approaches. I'll talk more about them in part 2. They're also the second half of the tutorial. And so I hope you enjoyed this lecture, and I hope you enjoy part 2, which will also be posted shortly.